I have already mentioned that the uniform 0-1 distribution is of great importance theoretically in probability theory. Now here is the first interesting fact, which is quite unexpected about uniform 0-1. I am stating it in the form of a theorem. Let x be any continuous random variable, just any continuous random variable. I am not even claiming density exists, just continuous with CDF capital Fx. So capital F is a continuous CDF. Then something interesting happens. Consider the random variable f capital X. Now understand it carefully. X is a random variable and capital F is a function. It is just a real valued function of a real variable. In place of that dummy little x, I am putting exactly this capital X. So now this is a random variable. So this is a distribution. Can you guess what the distribution is? You might say, well, it depends on capital F. Surprisingly, it does not. Whatever capital you take, this will always turn out to be uniform 0-1. Pretty surprising. The only condition I needed to put on capital F is that it has to be a continuous thing. So start with any random variable continuous, you can arrive at the uniform 0-1 using this. So somehow the distribution function controls the behavior of x, and then you again apply the distribution function. The two distribution functions kind of cancel each other off, and you are left with something which is always the same, uniform 0-1. Let's take a look at the proof. I shall start by giving it a name, capital Y. Now you might be tempted to think I am going to use the Jacobian formula. I can't, because no one has told me that this capital F is differentiable. I did not say it corresponds to a density. Just continuous is all that I have, so I cannot use that condition. But I do have one fact, namely capital F is non-decreasing. It need not be a bijection, it need not be strictly increasing, but it is non-decreasing. So what do? I will try to find out the CDF of Y and show that it matches the CDF of uniform 0-1. We have already seen this is the CDF of uniform 0-1. So once I show that the CDF matches, since CDF characterizes a distribution, I will have finished the proof that Y indeed had uniform 0-1 distribution. Now as you can guess, these two are very easy to prove because capital F being a CDF can only take value between 0 and 1. So capital Y also must lie in the range 0 to 1. It may not take the value 0 or take the value 1, but it cannot go outside that. So if you take little y less than 0, then there is no way capital Y can be less than or equal to Y. So you get this. Similarly, if you take y greater than or equal to 1, there is no way capital Y can avoid being less than or equal to little y. So you will get 1. So these two cases are immediately proved. We are only left with proving this thing when y lies between 0 to 1. Now just observe that I might as well put this equality over here. That will really not matter. I will get the same thing, but it will help me technically in a moment. I start by taking any y in open 0, 1. Then I shall try to express it in terms of capital X. So this is probability capital Fx less than or equal to y. Since f is non-decreasing, what I want to do is I want to apply something like f inverse to both sides to come up with x less than or equal to f inverse of y, and I will say that the inequality is not disrupted because it is non-decreasing. The only trouble is non-decreasing does not ensure that it is strictly increasing, so it need not be a bijection. So that is the only problem. That's why I put it inside a cloud. That's what I dream. Now let's see with a graph what may go wrong. Now if the graph of capital Fx looks like this, here I have drawn it strictly increasing, and you have got y somewhere sitting between 0 and 1, I can immediately see that there is a unique point, call it b, where f takes the value y. So I can directly put b here. So fx less than or equal to y is same as x less than or equal to b, because it is non-decreasing. However, this is not the general case. You may also have a situation like this, where it is just horizontal over certain range, and it so happens you have precisely chosen that y where it is flat. Now it is not 1 to 1. So the question is, which value do I take? So the value y is taken over this entire interval. In that case, if you look at it for some time, you will guess that you want this very end point, because your aim is to make the statement that fx less than or equal to y means x less than or equal to something. So you will take the very rightmost point until up to which fx will continue to be less than or equal to y. So our aim is to find the rightmost point b such that fx is below y, or below I mean less than or equal to y. That motivates a rather technical definition to replace this f inverse y. I will define b as the supremum of all x for which fx is less than or equal to y. You are trying to continue less than or equal to y as long as you can. When you cannot, at the very rightmost point, you choose your b. Now, whenever you write such a thing, this is very obvious from the picture. How do you know that you can take supremum? You have to show that this is non-empty and bounded above. That it is non-empty is obvious because I took y strictly between 0 and 1, and I know it's a continuous function going all the way to 0. So you just pick something less than y and between 0, it is bound to cross that. So at least that point is definitely inside your set. You see why I chose y to be strictly greater than 0? This is precisely the reason why I did that. Similarly, how do I show that it is bounded above? Because y is strictly less than 1, you just take any value between y and 1. This is a continuous function going all the way up to 1. Some point or other, you are bound to cross that value, and that will give you an upper bound. Because obviously, if you take anything even larger, you will even go above. You can never come to y. Think about this point. So you see that this is a non-empty and bounded set. So this b is a nice real number. Once you choose b in this way, what will fb be? Just look at this graph and you will immediately see, because it is continuous, it has to be exactly equal to b, equal to y at that point. Now, if you remember the proof of intermediate value theorem that you did in analysis 1, you will notice it is exactly the same argument, because if fb happens to be a little less than y, then there is a gap, but f was continuous. If it happens to be above, then this itself will provide an upper bound, because when it went above, it crossed y sometime or other, so it will already, you will get a smaller upper bound. I am not writing down all the mathematical steps here, they are already in the class web page. It is more important to be able to visualize it than rather play with epsilons and delta. Try to visualize it, why going above will cause a problem and why going below will cause a problem. Once you have the intuition correct, look up the web page to see the exact epsilon delta argument. So the only thing that is left is fb must be equal to y, and now the proof is just straightforward. So now I write fx less than or equal to y is actually x less than or equal to b. That's exactly how I created it. X less than or equal to b, that is precisely f of b, because capital F is the CDF of x. And what is f of b? That is y. So we have shown that probability y less than or equal to y if y lies in 0 to 1 is y, which fills up the missing link. Now we see that the CDF of y is our familiar shape, 0 up to 0, goes up the 45-degree line and becomes horizontal after 1. So that proves capital Y must have uniform 0, 1 distribution. Here I have given you x, which is a continuous thing. It has even density to the power minus x if x is positive 0 otherwise. Your job is to find f of x. F is the CDF of x.